first the bond order, because we have a, if we look at this bond here, it's double and single. So the average of 2 and 1 is 1.5. Both of them are the same still. Both of them are 1.5 bonds. That's perfect. So this is how we show 1.5 bond. As far as the charge on the oxygen, we have a negative charge distributed over 2. A -1 charge distributed over 2 is going to give you -1/2 for each. This is good. And then you sum up the formal charges, and you get the net charge. The net charge is -1. One thing is, chemists will never write 1 here. Chemists will just write negative. So we don't bother with 1. Okay, the other thing is, and this is very sharp of you to see that if we just take that lone pair and split it into 1 and 1, then it works out nicely as far as distributing lone pairs. But there's something odd about quantum mechanics, and yeah, you're right. We've got we got this. We got two lone pairs fixed, and then we got a third lone pair. Well, what if we just split that lone pair into 2 individual electrons? Put 1 electron here and 1 electron here, then it's all evened out, balanced out. But what that makes is it makes something called if there's a single electron, it's an odd number of electrons. We call those species what? Free radicals. Free radicals. Free radicals are going to have certain characteristics. One of the characteristics they have are magnetic properties. When we have unpaired electrons, those have special magnetic properties called paramagnets. But this does not. So oddly enough, if we had single electrons here, oddly enough, you'd think this works out as it should, but it doesn't behave like this. And so you're right, I'd like to split it up like that, but what we're going to do is we're going to draw like a dotted line here to show that it's going to spread out, but everything's still paired up. And so you're right, that's pretty sharp doing that, but here we're just going to do this because we're going to just kind of ignore it, because I said the quantum mechanics is kind of complicated. And there are 2 versions of quantum mechanics that we use. There's the light version of quantum mechanics, and then there's the rigorous version of quantum mechanics. When we're doing Lewis structures, we're doing the light version of quantum mechanics. If we really wanted the accurate structure, if we did the rigorous version of quantum mechanics, we'd never get this. The rigorous version of quantum mechanics takes us straight to this. And the way we visualize it is a bit different, because the rigorous version of quantum mechanics would automatically, we wouldn't have to do this averaging. We wouldn't have to make 1.5. It would automatically come out like that, and the charge on the atoms as well would automatically come out. And so there's a word. Have you ever heard the word ad hoc? Ad hoc. You ever heard this? Ad hoc means it's after the fact. It's a fix after the fact. So I do all this work, and I come up with this, and hey, this doesn't match what's observed in nature. What's observed in nature, these 2 bonds are exactly the same. There's no difference in these 2 bonds. And these 2 oxygens are exactly the same. But these structures don't show that. And so the hybrid, the whole concept of the hybrid is an ad hoc fix. It's an after-the-fact fix of our quantum mechanics light version. And so the quantum mechanics light version didn't quite come up with the correct answer, so we're going to do an after-the-fact fix. And so this is what we're doing with the hybrid. We don't have to do this after-the-fact fix if we use the full quantum mechanics. All right, let's talk about the structure now. Okay, so we're okay with Lewis structures, maybe for bicarbonate. We're okay with this. Now, when we do Vesper, we do not do Vesper on this because it just makes things a bit more complicated. And so when we do Vesper, we just pick one of these structures to do Vesper on, one of the Lewis structures, not the hybrid, because the hybrid, when you look at this, how many groups, it would work, but it's just more complicated than what we want to deal with at this time. And so what we'll do is we're just going to pick one of these. So let's analyze the structure of this one. So we're going to analyze the structure using Vesper. And so when we do Vesper, we look for central atoms. This particular molecule is kind of complicated, so it has actually how many central atoms here. Central atoms are like something that bridges. Like this oxygen is considered central, however this hydrogen is not. So we don't look at the structure around hydrogen, we look at the structure around oxygen. So we're going to look at the structure around this oxygen. We're going to look at the structure around this carbon because it bridges atoms here. However, are we going to look at the structure of this oxygen? This is a terminal oxygen. This is a terminal oxygen. So we don't necessarily apply, but we can. But you do that Chem 1A here. So we want to know what the structure around this oxygen is, and we want to know what the structure around this carbon is. And so first, let's take a look at this oxygen here. How many groups of electrons? 4. Or groups, 4. What's the electron geometry? Tetrahedral. What's the angle for tetrahedral? 109.5 degrees. What's the molecular geometry? The molecular geometry would be the geometry of the bonded atoms. The bonded atoms will be HOC in this case. What's the HOC geometry? Is it also tetrahedral? A lot of people will say it's linear because it looks linear, but it's not linear. What is it? It's bent. And it's bent at 109 versus a bent at 120. Do you predict any distortions to this? Yeah. So we predicted maybe it's going to be bent at about 105 degrees. That's a guess. We have two bends. We have bent at 109 and we have bent at 120. Okay. All right, let's go to this carbon here. How many groups? 4. Okay, tell me what the 4 groups are. All right, 3 groups. A single, single, and a double. That's 3. A total of 4 bonds because the double counts as 2, but 3 groups. The electron geometry? Trigonal, right? Planar, trigonal planar. Correct. The molecular trigonal planar. What's the angle of trigonal planar? The angle of trigonal planar is trigonal planar is not 109.5, it's 120. The molecular geometry? Do the atoms follow the same geometry as the electrons do? Electrons are going to adopt a trigonal planar arrangement, but if you look at the atoms are in the same arrangement. The atoms are in the same arrangement, we call it trigonal planar as well. And trigonal planar should be 120. But there are going to be distortions. You know, so for example, this top one's going to be a little wider. This one's going to be a little wider. This one's going to be a little narrower. We talked about that before. And so the final step would be to try to draw this. Can we try to draw this now? When we draw this, we try to put as many atoms in the plane of the board. And so first let's draw the oxygen. And what does a tetrahedral arrangement look like? Tetrahedral is going to be 2 in the plane, 1 coming out and 1 going in. And so the 2 in the plane we'll put as the bonds. So we'll put the hydrogen up here and then the carbon down here. And that means what's happening with the lone pairs. 1 lone pair is going to come out, 1 lone pair is going to go in. Now normal lone pair out draws a circle like that. But if a lone pair is coming out, I'm just going to draw it as a solid circle, fill. And if the lone pair is going in, I'm going to draw it as a dotted circle. Yeah. So in plane, coming out, going in. Okay, then this carbon, what's the geometry of this carbon? Well, that's tetrahedral electron geometry. This carbon's going to have a trigonal planar. Trigonal planar would be something like this, where the angles are 120. What I'm going to do is I'm going to flip the double bond down here. It doesn't matter where I put it. Maybe I should have put it up there. Let me flip it back up here. So let's try to keep the angle at 120. And so all the atoms are in a plane here. So it's kind of flat. Except, you know, this hydrogen can pop out because there's rotation. And so this hydrogen can pop out and rotate like a propeller. But we can flatten it in the plane here. So single bonds can rotate. Double bonds cannot rotate. So just stuff like that. So this would be like the 3D or wedge, they're called wedge and dash diagram. So this is 3D. All right. Does somebody have their lab? Maybe not. The lab for well, let me talk about an advanced topic just a little bit. And that was the question with the symmetry. Symmetry, and the other topic is non-equivalent resonance form. For example, something like nitrous oxide, N2O. You know, N2O, we'd like to put a bridging. You know, oxygen likes to form a bridge like this, so maybe you could bridge 2 nitrogens like this. Or we could follow our rule. Our rule was that nitrogen, being the least a negative, should go in the center. Like this. Which one looks better to you? The oxygen in the center, it is like water, you know. We see oxygen bridge atoms all the time. So this one looks the best here. However, it turns out it's not. And let's just briefly go over why. Nitrogen is 5, oxygen is 6. And so we're going to have a total of how many electrons? We're going to have a total of 5, 10, 16 electrons, is that right? 16 electrons. So when we do this, oh, this is easy. We can do something like this. We complete the octet to the nitrogen, and that takes care of 16 electrons, but Oxygen's unhappy, so we need to do something about oxygen. What can we do? We can form double bonds. So one of the double bonds would be like this. And we'll have another double bond here. Now everybody's happy, correct? Does this look good to you? Well, that's following the rules, right? But everybody has an octet, but somebody's very unhappy in this. What's very unhappy?
Oxygen.
Oxygen. What's unhappy about oxygen? It's only got 4. It's supposed to have how many electrons? 6. So this oxygen is plus 2. So basically, and the nitrogens, what are the nitrogens? Nitrogens have 6. They're supposed to have 5. So the 2 nitrogens ganged up on oxygen took 2 electrons. Does that make sense to you? Which one's more electronegative, nitrogen or oxygen? Oxygen. So it doesn't quite make sense because oxygen's stronger in a tug of war for electrons, and yet it lost nitrogen. Not 1, but 2. And so these are what we call high formal charges. When we have high formal charges, those aren't good because those are like second ionization, third ionization energies. Those are very high. So high formal charges are unstable. So maybe we could generate maybe what we could do is we put 2 lone pairs over here. Maybe that could work. Well, that's not following our set of rules, so we'll follow our set of steps. Let's do the same thing over here. So we have 2 choices. One choice is, okay, nitrogen and oxygen are going to share evenly. That is evenly in support of the middle nitrogen. And so we just form 2 double bonds. This nitrogen donates a pair, this nitrogen donates a pair, we got 2 double bonds, everybody's happy. Well, what are the formal charges here? The formal charges here, this nitrogen is going to be plus 1, and this nitrogen here is going to be minus 1. So on the one hand, nitrogen versus nitrogen should be at a tie, right? On the one hand. On the other hand, well, which one's better, this structure or this structure? This one. This has lower formal charges. It's better. The best is if we get rid of formal charges entirely. I mean, that would be the best. Well, what if it wasn't even? What if nitrogen sacrifice? This oxygen doesn't want to sacrifice any electron. Right. If this oxygen doesn't sacrifice, let's say the nitrogen is going to sacrifice 2. And so this lone pair is going to come here, this lone pair is going to come here. And so nitrogen is the only one that's going to support the middle nitrogen. The oxygen doesn't. Okay, now what are the formal charges here? Yeah, in this case, we have a positive on the nitrogen and a negative on the oxygen. And so what this boils down to is this. What it boils down to is it's pretty much impossible to get rid of the formal charge and maintain an octet. When it's impossible to get rid of the formal charge and maintain an octet, we try to minimize the formal charge. When we're minimizing the formal charge, okay, we might run into a scenario like this. Now what we have to do is we have to think, which one do you like better? The negative charge on the nitrogen or the negative charge on the oxygen? negative charge on the oxygen. So we predict this one to be more stable. But the problem here is this. The problem here is that how big of a difference is there between nitrogen and oxygen in terms of electronegativity? Yeah, 0.5 according to the Chem 1A book. Let me just check with the Chem 4 book. In the Chem 4 book, it's not even 0.5. In the Chem 4 book, the difference in electronegativity is 0.4. And so they aren't that different. Yes, I expect the negative to be more stable on the oxygen, but nitrogen is no, what do you say, weakling, or it's not a slouch. Nitrogen's got some strength, right? And so both nitrogen and oxygen. So if there's a tug of war, it's not a one-sided victory. If there's a tug of war for this extra electron, it's going to be more of a tie. However, oxygen is stronger. These are what we call inequivalent resonance forms. Whereas, remember the resonance forms I automatically eliminated for bicarbonate, those were way off in terms of energy. These are not way off in terms of energy. Since nitrogen and oxygen aren't that far apart from each other, they're pretty close, then these are inequivalent resonance forms. Or non-equivalent resonance forms. And so I wanted to just touch on two topics. One, symmetry doesn't always win. Here this is symmetrical, but this structure is worse than the asymmetric structure that we generated here. So symmetry doesn't always win. And two, I know this slide says equivalent resonance forms, and that's a good guide. However, when you get into Chem 1A, one of the first structures you'll hit is a structure with inequivalent resonance forms. And so it says here, resonance structures, two or more equivalent. This should be modified, two or more equivalent or near equivalent Lewis structures. The other Lewis structures that we generated for when we put the double bond over here, that was so high up in energy we could automatically eliminate it. That wasn't anywhere near equivalent. It was significantly higher in energy. Okay, so we're going to do the same thing here. We're just going to continue, right? End early. Are you guys okay with that?
Yes.
Okay. So we're going to just get more practice with Lewis structures and Vesper. And so let's write some structures up here.